So the name of the chapter is the properties of the pure substances. So if we look into the slide very carefully, so what is pure substance? So pure substance, so what we are going to discuss, the concept of pure substance, the physics of phase change process, and how to plot phase change process in a PV diagram or maybe a TV diagram or maybe a PT diagram. These are basically those independent intensive properties to locate those diagrams, and you can carefully look that these are not capital V, these are small v's, because you need intensive properties. And also we'll learn about what is called PVT surfaces. And in the next day we are going to learn that how to find out the properties of current state from the property table. So learning how to read property table, that is also an important part of this chapter. So let's look into the topic. So what is pure substance? Pure substance is a substance that has a fixed chemical composition. So like, what do you mean by that? So fixed chemical composition means that if you take any sample, small sample from anywhere of that substance, and if you took another sample from that object from any other space, if you compare these two samples, you will see they are chemically perfectly identical. So this will be called as a pure substance. So you can say that homogeneous, you can say, is something like a similar kind of thing. So suppose air, if you consider this air, so if you consider air, air is basically a mixture of several gases: nitrogen, oxygen, then carbon dioxide, carbon monoxide, some inert gases. So but if you take any sample from any space, it will show you kind of a similar composition, so it is a pure substance. So what is not a pure substance? So now we need to understand that what is not a pure substance. So can you give me an example what is not a pure substance?
Sir, gel, any type of gel.
Gel. Gel is like, are you talking about that hair gel for keeping your hair straight?
Yes, sir.
Sir, mixture of oil and water.
Mixture of oil and water. Okay. Any gel. So gel, like if you consider that gel has small particles, just like your toothpaste, there are some cooling crystals. So if you take a small part of that, which part maybe have a cooling crystal, and the other part, that part may not have a cooling crystal. So just like that, if you are talking about that kind of a gel, so that is not a pure substance. Just like what he was giving some example, like a oil water mixture. So if you have a oil water mixture, due to the density differences, what will happen, that it will settle in a different composition. So if we take a simple part of that, it may happen that the composition is not homogeneous. Now suppose if I give you one example, suppose if it is a water and water vapor mixture, is it a pure substance? If there is a container and in the container there is some part is vapor, some part is water, so can we consider this as a pure substance? Mixture of water and water vapor. Any opinion?
Yes, sir. Pure substance.
Yes, sir.
Pure
Sir, component একই থাকবে।
H2O থাকবে।
Perfect.
Chemical
Perfect.
composition.
So it may happen that the phase may be different. The liquid water is basically liquid, and the vapor, which is basically a gas. But if we take a small sample, they will show you the same H2O, that two hydrogen molecules, and that is basically bonded with a oxygen molecule. So it doesn't mean that to be a pure substance, it should be always in a same phase. It may be in different phase. Just like I'm giving some complicated example. Suppose there is a container. In that container there is some air, and what you are trying to do, start to cool down that air. So what will happen after a certain time, if the temperature is very low, what will happen? The oxygen will convert into liquid, is that right? And the nitrogen will also convert into liquid. Is it okay? So now in that container, some liquid nitrogen is there, some liquid oxygen is there, and the remaining part is filled with the air itself at gaseous phase. This system is not a pure substance, because if we take a sample from the liquid, in that liquid you have only nitrogen and oxygen. But if you took a sample from the air, it will have oxygen, nitrogen, or maybe some part of argon, maybe some part of dust, some part of aerosol, or maybe suspended particle. So the composition of gaseous air and the composition of liquid nitrogen and the oxygen, they are different. So in that case, we cannot say that the mixture of liquid and gaseous air is not perfectly pure substance. Maybe if I give you another example, suppose consider about a distillation process, like you have different levels of different mixture of alcohols, maybe some alcohol A, some alcohol B, and some alcohol C, and you are heating that alcohol. So what will happen? Some fume will form, some smell of alcohol will generate over there. So there is a phase change process. Now if we take a small sample from that alcohol vapor, and if you take a small sample from that liquid, you will see they are different, because the boiling point is different. So if someone having a lower boiling point, that will evaporate more, and if someone having a high boiling point, that will evaporate less. So I am sure that you are aware about boiling point. You know that what is boiling point, okay? Just like for water, 100 degrees Celsius, 1 atmospheric pressure is my boiling point. So if you are heating alcohol, and if there are 3 alcohol are mixed somewhere, and it may happen that they are perfectly mixed, but whenever you are heating it, some part of the alcohol is being evaporated very fast. So in the vapor, the composition of that alcohol increases, and the other alcohol which is having a higher boiling point, that will evaporate lower. So what will happen? At the fume or the vapor, the initial alcohol will have a higher percentage, and the later high boiling point alcohol will have a lower percentage. So if we compare these two fractions, you will see the composition changes. So this is basically the definition of a pure substance. So we understood what is pure substance, and we also understood that what is not a pure substance. So just like I'm just trying to recapitulate. So
sir, I have a question.
Yeah.
Is alloy a pure substance? Any kind of alloy, metal alloy?
Yeah, we can say it is a pure substance if it is perfectly homogeneous. If it is perfectly homogeneous.
Okay, sir.
Now, like suppose the problem, you have asked that question. So if the alloy, if it is in a solid phase, it is a pure substance. If the alloy in perfectly liquid phase, it is perfectly pure substance. But if a alloy is slowly melted, maybe some part is the solid and some part is the liquid. If the melting point of this alloy, the composition elements have a different melting point, it may happen that liquid may have some different percentage and that solid may have some different percentage. Suppose just consider that you have, I'm again maybe elaborating that if A is there, B is there, A has a high melting point and B is having a low melting point. If this alloy is started to melt, what will happen? If A is having a lower melting point, it will melt. So in that liquid part, you will see that the alloy A is more. So that whole system cannot be called as a pure substance. Do you understand? Or it is a little bit complicated?
No, sir, it is similar to with the that alcohol example,
exactly.
kind of.
Exactly. So whenever there is a mixture, it is changing its phase. It is not very good to consider it as a pure substance. But if it is a single phase element, if it is a single object, then you can, the vapor and the liquid both can be considered as a pure substance. or whenever it is in a single phase, like if there is no possibility of phase change, it is, you are free to consider it as a pure substance. Only you have to ensure that it should be homogeneous. So if I try to define it, a pure substance has a homogeneous or a fixed chemical composition throughout. It may exist in one or more than one phases, but the chemical composition is the same for all phases. So these are the things that I'm trying to say. So just like liquid, water, solid, vapor, ice is also a pure substance. The ice, liquid and the vapor, they comes under a same pure substance, that is H2O or maybe water. So this is the introduction of pure substance. So also the homogeneous substance. So basically now the other important word I have here mentioned, maybe you have understood what is basically called a phase. So what is phase? So you are also from electrical background, so it is little bit complicated. So I am talking about the phases of a substance. Okay, so I am not talking about the phase you are interested with. Okay, so like 3-phase, 2-phase, 1-phase motor, 2-3-phase motor. I have no idea about those phases, but I have very limited idea about these phases. What is that? Phase is basically defining is kind of a state, like a state of a system. And a phase is identified as having a distinct molecular arrangement that is homogeneous, and throughout from other phases it can be easily identifiable by a separated boundary. Like what I'm trying to say, suppose if you have a container, in that container some water is boiling, so the water is basically liquid water is basically the one phase, and the vapor, that is also in another phase. There are two phases. One phase is the liquid and the second phase is basically the vapor. And what is phase? The phase should have a fixed interface, like it should have a fixed boundary. So we can look at the water level is basically the phase boundary. It is basically the boundary between two phases. So if suppose you can see that in a container, vapor, water and ice are present simultaneously, you can say this is a 3-phase system. 3 different phases are present. So now what is phase? Phase is basically, I told you that it is basically defining a specific molecular arrangement. So this molecular arrangement is basically created due to the molecular attraction forces. So if the attraction force is very strong, the molecules will remain in a compact, rigid structure. It's like we can imagine this intermolecular forces as a spring force. These spring forces are combining these surfaces, these molecules, and it is creating a rigid structure. Whenever this spring force is very high, if there are two molecules, if these two molecules are connected by some springs, and these springs, if the stiffness of the spring is very strong, these molecules are not allowed to move freely. So at that state can be defined as a solid state or the solid. And if there are two molecules, the spring force is there, but they can move relatively to each other, so they can flow over each other. So this is basically defining the liquid state. And what is gaseous state? Where these forces are almost negligible. So any particle is free to move each other in any direction, and they are even bombard each other, just like that right figure. So every time they are colliding and exchanging velocities and momentum every time, and also the temperature. So it is happening every time. So this is basically the phase. So the 3 common phases we deal in thermodynamics are basically the liquid phase, the solid phase and the gas phase. Where the attracting forces are very strong, those are basically called the solid phase. If the attraction force is not so high, and the molecules are free to move relative to each other, but they are not independent. There is a connection between these two molecules, and they can move relative to each other. This is basically the liquid state. And when they are completely free, and is basically extremely disorganized system. So that system is basically called the gaseous phase. So we understood what is called phase in a thermodynamic point of view. Okay, so now I told you that why we are going to study this subject, to understand what is phase change. What is phase change? So if I consider, if you look into this figure, so so if this is a gas phase and this is the liquid phase and this is the solid phase, so the gas can be converted into liquid, or maybe liquid can be converted into vapor. So whenever the liquid is being converted to vapor, we call it this process as vaporization. This is known to us. I'm just revising. And when this gas is converted into liquid, it is basically called condensation. So whenever liquid converted into vapor, it is basically called vaporization. Whenever the gas is converted into liquid, it is basically called the condensation. Now, it may happen that the solid can be converted into liquid, maybe due to some heat addition, just like your ice cream melts. So this is basically called melting. You already known to this verb, melting. And if you have liquid and this liquid is rejecting heat and converting into solid, this may be called as a solidification, or maybe the freezing process. Freezing is more accurate, more known to us. And there can be another possibility where the solid can be directly converted into gas phase, or maybe the vapor phase. This process is basically called EE. So E is basically called the sublimation. And there can be another reverse process where gas can be directly converted into solid. This is basically called the deposition process. Now, can you give me an example of sublimation process?
Sublimation of camphor or naphthalene.
Yeah,
Naphthalene.
perfect. So basically, if you consider the naphthalene, now the question, there is a one critical question, that is it possible to convert ice into vapor directly? Or maybe sublimation process is possible for any other substances, for iron, or maybe some other object, or maybe can we see that can we just see that the liquid iron vapor, can we see iron vapor, that liquid iron is converting into vapor? Is it possible to have like this?
Not in general cases, but we can create that that kind of environment or that kind of system to for that process, like increasing the pressure or something like that.
Exactly. Perfect. So perfect, correctly pointed out that whatever we are considering, this boiling, this solidification, whatever we consider in practical life, we always consider in terms of the normal temperature and pressure. Just like you can see sublimation of camphor at normal temperature and pressure. Even it is possible to see sublimation of ice at maybe that some specific temperature and pressure. So everything can happen, like sublimation of water is possible, or maybe vaporization of iron is also possible. It depends upon what conditions you are creating. So for every substances, you can get these processes. So we are looking to this phase change process. So, but one thing we understood, that for phase change process, two parameters are most important. One parameter is the temperature, one parameter is the pressure. These two are the critical parameters that determines this phase change process. So let's look into this. So just take a most common example. Just think about this experiment that you are performing. Just you consider yourself as a scientist and you are performing this experiment. So suppose if you have a piston, and in that cylinder there is a piston, and inside this piston cylinder there is some amount of water, maybe some fixed mass, maybe suppose if considered as a 1 kg, and the initial pressure of this system is 1 atm. and the temperature is 20 degrees Celsius. So one atmospheric pressure and 20 degrees Celsius temperature. This is the state 1. Okay, any doubt up to this much? I will discuss this slide, but whatever we have discussed till now, if you have any doubt, you can point it right now, or I will continue. But please pay attention. These few slides are very important. If you have any doubt, you can stop me. I can repeat. Shall I proceed? Is there anyone who is listening? Shall I proceed?
Yes, sir.
Okay. So hopefully understood that whatever we have discussed till now, I am assuming that you have understood. Okay. So now I am entering one virtual experiment. I am performing this experiment. I have considered some fixed amount of water. I am heating it. The initial temperature is at 20 degrees Celsius and the pressure is 1 atm. Now, what is the property of this water? This water is existing at liquid phase, and I am calling it as a compressed liquid. Why I am calling it compressed liquid, I will explain it later. But what do you mean by compressed liquid? Compressed liquid means I am talking about a liquid which is far away from a state where it is about to vaporize. This compressed liquid is not going to vaporize right now. Are you agree with me? Because the temperature is 20 degree and the pressure is 1 atm. So this liquid is not going to vaporize right now. It may vaporize. Let's see when it is getting vaporized. So slowly, what happens? You can see the burner. So you are slowly supplying heat. The temperature will gradually rise, and after some time, the temperature will reach to 100 degrees Celsius. It will be big. Initially, it will be 20, 30, 40, 50, 60, 70, 80, 85, 90, 100. So why 100 is important? Because it's like a century? No, it may be anything. So just like this 100 degree is so crucial. Why this 100 degree is so crucial? Because this is the point where this liquid is about to vaporize. If you add some delta unit of heat, the vaporization will start. Now, if we calculate the liquid mass will be less than the initial liquid mass because some part is already converted into vapor. If we add some delta amount of heat. So this state is basically called the saturated liquid state. So I have discussed about two states. One is the compressed liquid state and the other one is the saturated liquid state. So we gradually heated that liquid and the pressure remained constant. This is an isobaric process. How we are maintaining the pressure? Because I am keeping a weight, and this is basically the weight of this piston. So the weight of the piston is governing the system pressure. If you add some weight over this piston, then only the pressure is going to increase. Otherwise, the pressure will remain constant. So it is basically a constant pressure process. You are not going to add anything over it. So it is a constant pressure process. Now, I am continuing this process. So if I continue this process, if I slowly heat that liquid which was about to vaporize, if we continue to heat it, what will happen? Some part of that liquid is going to vaporize. Is that right? So as you are heating, that some part of the liquid is slowly getting into vapor phase, and the liquid level will start to slowly gradually fall, and the volume of that container, that is also going to increase because the density or the specific volume of vapor is basically higher. This is basically kind of an expansion. But you also understood that whenever you have that liquid, whenever you start to heat this liquid, there is also some expansion. But that expansion is basically the liquid expansion. Is that right? Suppose if you have like 500 ml liquid, if you start to heat it, the volume will gradually increase, very partially. Maybe if it is 500, after maybe reach to 100 degrees Celsius, it will be maybe 550 ml. But there will be a slight change of volume because of this expansion. But whenever you start to heat it further, the liquid volume will decrease. But liquid volume is decreased because the liquid quantity is also decreasing. It's not like the liquid is compressing, but liquid quantity slowly start to decrease, but the volume of the vapor, that will increase sufficiently. Now, one common question, like the water temperature is 100 degrees Celsius, but what is the temperature of this vapor? Is it more than 100?
And no, 100.
It is 100 degree. Are you sure?
Yes.
Everyone is sure?
Yes, sir.
Yeah, because if it is 101 degree, then it will start to heat it. Finally, the whole system will come to equilibrium. So the vapor temperature is also 100 degrees Celsius. The temperature of the liquid and the temperature of the vapor, they are same because there is a physical contact. So there is a continuous heat transfer. So it will try to keep everything in a thermal equilibrium. I told you what is thermal equilibrium. Now, if we gradually heat it, after some time, the liquid layer will slowly come down and more amount of vapor will generate. But during this process, the pressure is still constant, 1 bar. So after some time, the whole thing is converted into vapor. Okay. Now it is 100 degrees Celsius. The whole thing is converted into vapor. This is called saturated vapor. You got my point? This is called saturated vapor. What is saturated vapor? If we reduce 1 unit of heat from this vapor, some liquid will condense. If you take some heat out of the system, as you are taking out heat, so some part of the vapor will gradually condense and convert it into liquid. Where in the previous case, it was about to vaporize. And this case is basically about to condense. So it is already completely converted into vapor. Okay. Now you reach to the state 4. Now we'll go to the state 5. So if we further heat it, now you will see the temperature will gradually increase. And it will reach to 110, 120, 130, 140, 200, 300, 400, 500, anything. How much heat you are going to supply. So do you understood the state 1, state 2, state 3? So the state 1 is basically called the compressed liquid. State 2 is basically called the saturated liquid. The state 3 is basically called saturated liquid vapor mixture. Okay. And the fourth phase or the fourth state is basically called the saturated vapor. And after reaching the saturated vapor, if we heat it further, as the more heat is transferred, the temperature of the vapor will start to rise, and this is basically called the saturated vapor. Okay, superheated vapor. Sorry, so got distracted. So basically, it is called superheated vapor. Okay, so now if I try to plot this temperature with respect to the volume. Volume means the specific volume. How to get the specific volume? You know the initial total volume. You will simply divide by the mass. If we know this total volume, and I will simply divide with the total mass. So I will get my specific volume. So we understood that as we are heating, my volume is increasing and the mass remain constant. So finally my specific volume is changing. Now if I try to plot that how my temperature is changing with my specific volume. So if this is my V, so as I am heating it, my temperature is increasing. So this is the initial state 1. So this is 1. This is at 20 degrees Celsius. Volume is minimum. As you are heating it, there is slight liquid volume expansion. So there is a volume expansion, there is an expansion. So this is basically the volume expansion. And there is also an increment of temperature, because as you are heating it, it is gradually increasing the temperature 20, 30, 40, 50, 60. But whenever it is reaching to 100 degrees Celsius, the temperature becomes constant, because the whole liquid is converted into saturated liquid where it is just about to vaporize. We know it is basically called the saturated state. So it is converted from compressed liquid to the saturated liquid. After that, if you continue to heat it, what will happen? The temperature will remain constant. Why the temperature will remain constant? Because it is the boiling point of water at 100 degrees Celsius. This is known to all because it is only the sensible heat. That time we do not have any kind of specific heat. The temperature will remain constant. So after some time, so what will happen? That the temperature remain constant, but as the vapor, the percentage of vapor is increasing, my volume is also increasing rapidly. So this is the increment of volume. After that, it will completely converted into vapor. It is basically called the saturated vapor. After that, if we further heat it, the volume will increase along with the temperature will increase. Both will increase, just like what happened. But here, the slope, here the temperature increase more and the volume will increase less, because the expansion coefficient of compressed liquid is very less. But as you are reaching there, the temperature, for a unit change of temperature, the change of volume is higher because the expansion coefficient is high. So hopefully you understood what I'm trying to say. So what will happen? This is basically representing one path, one process. Okay. Now during this process, what is constant? Which variable is constant during this process?
Pressure.
Pressure. Very good. So this curve we can obtain for a single pressure. Now, if I repeat this experiment for a different pressure, just like what I have done, I simply put one weight or batkara over this and repeat the experiment. So what is going to happen? What is your expectation? What is your expectation?
Boiling point will increase.
Boiling point will increase. How you can say that? Do you have any example of that?
Sir,
It will
when
decrease.
pressure decreases, the boiling point decreases. Just like at the top of mountain, the boiling point of water decreases due to the drop of pressure. And
Well, perfect. Perfect. Just like we know that every Sunday or maybe once in a month, Sunday we use pressure cooker. Is that right? Some
Yes,
of
sir.
them, maybe most of them. So what pressure cooker does? It increases the pressure so that the boiling point increases. If the boiling point increases, the cooking temperature increases. If the cooking temperature increases, the what will happen? The cooking process will become faster. So it will easily cook the food. So just like that. So what will happen? Whenever we are going to change this pressure to 1 atm to 5 atm, this line may be somewhere, this phase change line will be somewhere there. So if it is happening at 5 atm, the horizontal line will lie somewhere there. If you are doing at lower pressure, the horizontal line will be somewhere there. Do you get my point? What I'm trying to say? Because the phase change temperature. So this is my phase change temperature. At higher pressure, my phase change temperature will be higher. At lower pressure, my phase change temperature will be different. So if I check that this is known as the saturation temperature and saturation pressure, like the boiling point is strong function of pressure. As your pressure increases, your boiling temperature increases. Why it happens? Like already you know, but I'm just elaborating. Like suppose you have a container, and in that container you have some part of liquid. Now if we start to heat it, what will happen? Basically you are supplying energy. This energy will be transferred into the molecules of the liquid. If the molecules of the liquid have enough energy, it can break the intermolecular forces and become independent. After it become independent, it will convert into vapor. Now what pressure does? Pressure always resisting this phase change process. No, just sit there. But you are supplying heat, it is saying go and become vapor, and pressure is basically always pushing it. Is that right? Just like your cold drinks bottle. In that cold drinks bottle, the carbon dioxide is basically pressurized inside the liquid. Now whenever you open the cap, that the pressure released, so the air which was basically mixed inside that soda, so that comes out, pops out. So the same thing is going to happen here. Whenever you are increasing the pressure, you need to supply more heat to convert into vapor. But whenever this surface is very free, it is easy to move any direction. So it is easy to move, so you need lesser heat to transfer into vapor. Hopefully you understood. So if I try to see that, if you see at saturation pressure 1 bar, your boiling point is 100 degrees Celsius. Okay, 1 bar is 100 kPa. If your pressure is around 500 kPa, your boiling point is 150 degrees Celsius. Okay, so your boiling point will change. So now this is just information, this is already known to us. I am giving one example how it happens. So if I just repeat a few sentences, like one we know, which one is latent heat. So what is latent heat? This is known to us, the amount of energy absorbed or released during phase change process. What is latent heat of fusion? The amount of energy absorbed during melting, or it can be called as, it is equivalent to the amount of energy released during freezing. So if you are going for a freezing, you need to extract the heat. If you are going for if you are going to melt it, you need to supply energy. We know what is called latent heat of vaporization. So if you are going to convert from liquid to vapor, you need to supply latent heat of vaporization. And if you are trying to condense it, you have to extract the latent heat of vaporization. So these are the terms we are already aware of. I am just repeating if you have forgotten this. So now this is very interesting. So this is the same curve. This is the initial curve, which one already there. Now I have repeated the same experiment for different operating pressures, and it was found that the line will look like this. Why this line will look like this? This is just experimental observation. We found like this. Everywhere there is this is the compressed liquid. After that you start to heat it, it is converting into saturated liquid. The corresponding phase change temperature will change according to the pressure, and after that there will be a phase change process. During that, the volume will only the volume will increase, and after that there is a superheating phase. So saturated vapor will be converted into superheated vapor. But there is one interesting line. This line is very interesting. This line is basically called the critical point. If your initial pressure is enough high, if we start to heat it, there will be a case where there is no kind of horizontal line. The whole liquid will be converted into vapor, or maybe there is a smooth phase change, but below to that point everywhere there is a horizontal line, and this part is saturated vapor, this part is two-phase zone, and this part is the compressed liquid. So if I try to join this point, I will get this diagram. In this diagram, this is basically called the dome or the saturation dome. Beside the left side of this line, everything is basically compressed liquid zone. Inside this zone is the saturated liquid vapor zone, and right side of this zone is the superheated vapor zone. And how this curve is constructed? By repeating the previous experiment for different pressure, and finally we will get this curve, and this curve will have a special point. This point is called the critical point. Above this point there is no saturated vapor mixture zone. There is nothing called a mixture zone. Everything will convert smoothly, like an abrupt thing, just like this curve. If P is greater than P critical, it will directly convert. If it is less than P critical, it will convert it like this. And if it is exactly critical, there will be a single point it is going to touch. And that point is basically called the critical point. What is the definition of critical point? Critical point is the point at which the saturated liquid and the saturated vapor, the states are identical. Here, saturated liquid state, this is my saturated liquid state, and this is saturated vapor state. But at this point, the saturated liquid state and the saturated vapor state, they are identical. So this is the definition of critical point. But what we finally found out, that if I know the temperature and the specific volume of any water vapor mixture, if I know the temperature and the specific volume of water vapor mixture, if I know these two values, I can locate the point. And if I locate the point, I can specify that what is now its present state. If the points lie somewhere there, I can say it is a mixture. If I found the point, if I found that the temperature is 80 degree and the volume is suppose 0.2, so I can find out that this point lies somewhere there. So before physically looking into the state, simply plotting this point into the graph, I can find out that this is basically the saturated liquids, the subcooled or maybe the compressed liquid state. If I locate the temperature and the specific volume,
the last point I will repeat করবেন
follow
the last point I will repeat করবেন
last point বলতে
ওই যখন মানে যদি আপনি স্পেসিফিক টেম্পারেচার আর ভলিউমটা মাস দেওয়া থাকে তাহলে
okay, so what I was trying to say, that this is the experiment was done per unit volume. So it is basically the specific volume per unit mass. So what is going to happen, that if I know the temperature and the specific volume, someone told me that sir, someone called me and he called me that sir ye batao to sir, I have one liquid vapor mixture and the mixture temperature is suppose 200 degree and the pressure is 20 bar. Sir, can you tell me that this is in liquid state, this is in vapor state, or this may be a mixture? Simply, I will take out this diagram. This diagram is already given in your textbook. So I will simply take out this diagram. I will locate the temperature. It is 200 degrees Celsius. This is my 200 degree temperature line, and I will locate the volume. I will locate the volume, and if it is intersecting somewhere there, I will know, I will call back him and I will say that you have a mixture. So simply someone did these experiments and tabulated those graphs in a textbook. So simply knowing those values, you can identify that what is the. But suppose if I told you that I have 80 degree water, if I told you that I have 80 degree water, what is its state? If someone called me and tell me that I have,
it can't be specified. We have to know two parameters.
some water which is having a temperature, if someone called me and tell me that I have some amount of water which is having a temperature 80 degree, what is its state now? Liquid, vapor, gas?
Cannot tell because pressure is not specified.
Exactly. If he told me that I have that water at room temperature, room pressure, I can tell you that that is liquid. But if he is not mentioning the pressure, I can't locate. So that basically that's why this curve is constructed. This curve can tell you at any instant if you have a mixture or maybe a single phase or maybe a superheated phase. If we simply mention the temperature, it will, if you simply mention the temperature and the pressure, it will locate that point. So this is the way we can get this diagram. TV, this is basically called the TV diagram. Okay. So now, similarly, we can construct a PV diagram. Just like suppose if you have some amount of liquid water and it is at some temperature 150 degrees Celsius and pressure at 1 MPa. Now, if we slowly reduce the weight, so what will happen? What will happen? That just like what happens in mountain. So suppose if you have water at 95 degrees Celsius and suddenly you took the shoes of Gupi Bagha and clap it, Darjeeling, or maybe some high altitude. After reaching that altitude, you will see that 80 degree or that 90 degree water will start to boil, because at that pressure the boiling point is lower. So at that low temperature, at that pressure, the 80 degree is the boiling point, or maybe the 90 degree is the boiling point. So we know that if we remove weight, the operating pressure will slowly come down. If your operating pressure is slowly come down, it is more prone to boiling. But if we add weights, it is not going to boil right now. You have to supply more heat for that boiling. So if we simply repeat the experiment and try to plot in a PV diagram. In the previous case, you have plotted the diagram in a TV. Now you are going to plot in PV. The diagram will look like this. So you have some liquid, you slowly reduce the pressure. If you reduce the pressure, after some time, what will happen? It will reach to its boiling point. Because we know that if we reduce the pressure, what is going to happen? It is more about to boil. So after some time, it will boil. Whenever the boiling will start, we know that the pressure will remain constant. After some time, it will become vapor. After that, if we further reduce the pressure, that vapor will become more free and it is finally converted into superheated vapor. So it is, the chances of condensation will reduce. So it is becoming more free vapor. So it will becoming superheated vapor. So now if we draw this experiment for different temperature, Now this process, during this process, I am kept my temperature as constant. It is an isothermal process. Like if you have a container, you keep the temperature constant, slowly removing the pressure, slowly decreasing the pressure. What will happen? If the pressure is sufficiently low, the same liquid is about to boil. So it is basically boiling a liquid without adding heat. Are you getting my point? So by two ways you can achieve boiling. One way you can supply heat, boiling temperature, the liquid temperature will shoot up to boiling temperature, then the phase change will happen. Or maybe you keep your temperature constant, simply reduce the pressure. After reaching to a certain pressure, at that temperature, the saturation pressure will match to each other. That time also boiling will happen. So that boiling is sometimes called in cavitation. So that is basically a word in industry, that it may happen that 40-degree temperature at the exit of a pump, or maybe at an inlet of a pump, phase change can happen due to low temperature and also low pressure. That is basically called the cavitation. So I'm not going into that, but I am trying to say it happens. It's not like absurd. In pump, whenever you have a pump, there is suction in. In that suction in, the pressure is sufficiently low so that at that pressure, water at 35 degrees Celsius will start to boil and form small bubbles. These bubbles will collapse, and that is detrimental for the whole system. So that is why I am trying to say these things are common. So you can achieve TV diagram. You can achieve TV diagram like this, and you can achieve PV diagram by simply reducing the pressure at isothermal condition. And if we connect these lines, it will form this saturation dome. So we already know that what is the saturation dome in TV diagram and PV diagram. So up to this much I want to discuss. So if you have any doubt, I can clarify it and stop for today. So please clarify your doubt. If you have no doubt, you can still wait, because some of your friend can ask some doubt and that can add some funda to you. So just listen to stay for a few minutes and then you can leave. Yeah, I got one question. The change in melting point is a difference pressure less than the change in boiling point. The change in melting point in different pressure is the change in boiling point. That is, I'm not getting your question. Like melting point and the boiling point. Okay, melting point means you are talking about the solidification or the melting process, and whenever you are talking about the boiling point, you are talking about the liquid to vapor conversion process. But what is the question? The question is the change of melting point, different pressure is less than. Okay, so I have not yet discussed the solidification process till now. So I will discuss whatever is the question that you have asked, that I will going to answer in the next class. So if I show you that what he is trying to say, that this is basically the solidification procedure that I will discuss. So this is basically the pressure versus temperature, and this line will determine how the phase change will happen. This part I will discuss in the next class. And there is also a twist, like some liquid expands, some liquid contracts. So there are some issues. So I think I'll be answer this question in the next class. Devargo. Somewhat I understood your question. You are trying to say that the response, the effect of pressure on the boiling point and the effect of pressure on the melting point, these two are the different. Why there is a magnitude difference? So whatever you have written is something close, but I will elaborate in the next class. Do you have any other question?
স্যার স্যাচুরেশন ডোমের লেফটে
হ্যাঁ,
লিকুইড
লেফটে
পায়,
লেফটে
লেফটে যদি কোনো একটা পয়েন্ট নিই সেটাতে কম্প্রেস লিকুইড পায়,
হ্যাঁ,
আর রাইটে নিলে সুপার হিটেড ভেপার পাচ্ছি। মানে আমি বলছি ডোমটার ওপরে কি ওই দুটো স্টেট
exactly. If you go above that the dome, everything is equivalent. There is no kind of a separation between these two. There is no kind of a separation between these two. Just I want to just explain something. Let's try to understand. Hopefully I'll be explain it. So just I consider one thing. This is very, very crucial. Like what I'm going to say is very crucial. So if I take a new slide, if you wait for 5 minutes, I think we will close. In between we will close. So if you have patience, you can wait for 5 minutes. Within 5 minutes we will everything we will do. Suppose this is the pressure and this is the temperature, and you got one PV diagram like this. So you already know how we got this diagram, and my saturation dome is somewhere there. Okay, if you go to some sorry, I made a mistake. So this is volume, eraser. So so this is my PV. So if we construct it for some other temperature, my PV will look like this. So what he was saying, that this part is my compressed liquid. Very good. This part is my superheated vapor. Now I am trying to say that if we perform it for something for higher temperature, this diagram will look like this. Okay, if we do it for some higher pressure, some higher temperature, this diagram will look like this. If we do it for some other temperature, it will look like this. If we do it for high temperatures, it will look like this. Can you identify these lines? What are these lines?
Boyle's line.
These are isothermal lines.
Ideal gas.
Isothermal lines. PV diagram, PV equal to constant. So I don't know, do you get my point? So if we go to very low temperature and very low pressure, you will find this saturation dome. But if we go above, far away from this, you will become the ideal gas. I need to find one. Mouse will not work like this. Anyway, so basically these are ideal gases. Okay. So this part is ideal gas, and this part is basically the two-phase zone. So now what I'm trying to say, if we consider nitrogen, okay, nitrogen, this isothermal line is 40 degrees Celsius, maybe 30 degrees Celsius. But if we go to minus 170 degrees Celsius, you will reach to this line. So you will get a liquid phase change. But 40 degrees Celsius, it will behave like a perfectly gas. But the same thing for water. If we consider water, for water, this 80 degree, 90 degree line will lie somewhere there. Maybe the 100 degree line lies somewhere there. That's why you can see the two-phase zone at normal condition. But for nitrogen, to see the two-phase zone, you have to go very far bottom to see this. But every substances have this diagram. It depends where you are. Your atmospheric, if it is atmospheric somewhere there and you are in gas condition, you have to go very far down to reach there. And if you see liquid in the atmospheric condition, to convert it into gas, you have to go far away so that you can see the ideal gas. I don't know I have explained it properly or not. So somewhat, if you have still doubt, I can clarify it, but you start to think If you start to think and observe, then only we can answer this question. So someone understood this? Some of you, have you understood this?
Yes, sir.
Anyone who understood this, what I've tried to extrapolate, like how this ideal gases and the two phase, how they are different?
Sir, actually, you have proved the assumption that at high pressure and low volume, all the gases act like ideal gases and obey Boyle's law, Charles' law.
Somewhat, because high pressure, if you make it high pressure, in the form of in high pressure may not be very suitable for ideal gas assumption. High pressure, because
Sorry, sir. I may have made some mistake.
Low
Actually, that
pressure.
will be low pressure and high volume, because at that case, the internal attraction
Exactly.
of the molecules can be neglected.
Exactly. So, but here I am not going to say high pressure or low pressure or high volume. Here I am going to simply say that if height, as you move to the high temperature, it is going to become more ideal gas, because there is one issue with this, because this is low pressure. This is low pressure, this zone is low pressure, but still it is behaving like a liquid. So what I have tried to say, if I specifically say low pressure, I will not be perfectly correct, because this low pressure is also showing some kind of a liquid behavior. So it is better to say that if I summarize in a single word, that I should say that at high pressure, at not high pressure, at high temperature, it has more tendency to behave like an ideal gas. You start to read, I think a lot of doubts will come and we can discuss and clarify. If you have any other doubts, have you understood some part of the lecture? Maybe 50%, 60%? You need to observe more. Yeah, maybe only 2% are responding. Only Devargo is responding, and someone.
Yes,
Okay,
sir,
fine.
understood.
Some part you understood. Okay, so what I can do, I am posting one link in the chat box. So this is basically a YouTube link, and these are basically the NPTEL lectures. So these lectures are basically Professor S.K. Soam. So you can listen to these lectures. We have lost S.K. Soam just 1 year before. He was around 70 years. So he was also a alumni of Jadavpur University, I think so. So he was professor in IIT Kharagpur. So he has recorded several lectures on thermodynamics. So these lectures are very good. So if you'd like to listen few other lectures and parallelly want to study this subject along with this class lectures, so you can follow these lectures. And I think I have learned a lot of things from these lectures. I have listened to these lectures in my undergraduate days. So if you want to learn this subject more deeply, you can see I am recommending these lectures. So you can watch these lectures, and these lectures are very simple, and he is an extraordinary teacher. Like, he is the best teacher I have ever seen. So you can listen to these lectures, and based on that we can discuss and doubt. But watching these lectures are not compulsory. There are 32 lectures for this whole course. So you can watch this lecture. I'll definitely send you the PPT and the recorded lecture. I am all